Remember the PN junction we talked about last time? As a foundation of the modern semiconductor industry. Even though it's not a PN junction specifically, but there are all the PNNs being put together to form all the different transistors. So if you do this, it's just a simple diode. And what's the name of this region? Depletion zone. Sounds a better name actually.
I don't know if depletion region is kind of fun with that.
Yeah. What's the majority here? Remember? No, holes. Yeah. Here. Yeah. And then what about this one? On the right. Yeah. Here. And the electric field oriented like that, right?
Yeah.
And forms a electric field. And if you forward bias this diode, is this called forward bias or backward bias?
Forward bias.
Okay. This. Yeah, reverse bias, right? All right. So whenever you forward bias this diode, is the depletion region getting thinner or thicker? And what? Thinner, right? And when it's thin enough, the electrons will tunnel through and form a current flow in here. But actually, it's just electrons flowing backwards, right? And so this one also forms a potential barrier for this one because this is plus minus, right? But this power supply is plus minus in that way. So they are opposite, which means it has to overcome this potential. So the voltage being formed by this electric field is called built-in voltage. And for diode, for silicon, it's usually somewhere around 0.7 volts. Okay. And again, this forms the foundation of semiconductors because this is like a threshold voltage. If you increase V in here, the current, you can form an IV curve for the diode. Here's V in, right? That's a forward biased voltage of the V in. And if you start increasing the voltage, what's going to happen for the current? It has to overcome that 0.7 volts and then start getting a lot of current flowing that way, right? Because that's a diode like that. And what's this voltage? Yeah, that's like a threshold voltage. Even though this is not being used for the digital circuits, but it's the foundation of it. It forms the threshold voltage. Whenever the voltage is lower than that, it's considered as logic low. Whenever it overcomes that threshold voltage, it turns on the transistor, becomes logic high, right? So we got 0 and 1s for digital circuits. And that's partially why it's called semiconductors, because it's not really conductive. You have to overcome that threshold voltage in order to make it conductive. That forms all these modern electronics in your phone, laptop. That's the foundation of everything, pretty much. So how do you make a diode in the wafer? Right? So all these circuits, definitely you can use these rod diodes and plug into the breadboard and make the circuit, right? You'll probably do it in analog, all the labs. But we do have diodes in integrated circuits as well. It's just like this size, like 1.5 by 1.5 millimeter dimension, and you can integrate millions of these diodes in there. Billions, probably. How do you make a diode in that little area? How that happens? Yeah, if you look at the cross-sectional view of the wafer, what's the most popular substrate type? Right? Yeah, and you're thinking you're trying to make a PN junction. I mean, how these PN junctions are made on the wafer? You're thinking like, hey, P, N. Is this going to work or not? Why?
Because it's majority P-type on the outside, so right now.
And then you got a connector, right? And make a wire, go through metal 1, metal 2, metal 3 until the very top layer got an opening and wire bond it, right?
Yeah.
We just do it that way. It's a P junction. If you look from the top, right? Look from the top when you're doing the layout, you just put a P material here, put an N material here, and then you got two connectors, one from each side, and it's a P junction. It's not a way we do it.
Yeah.
Why is that?
Because P-type is still touching P-type, so you still have a ton of holes, and all those electrons you go to those holes instead of pushing over to the N.
Yeah, it's like the whole thing is a P.
Yeah.
But you have a P here as well, so this doesn't make sense because this has a connection with the P. It's usually a P plus, so this is shorted to the P substrate. So the whole wafer becomes the anode of the diode. You know what I mean? Why that is bad? Because usually the P-type, the substrate, so the whole wafer, the substrate, is shorted to ground or the lowest potential of the circuit. This is another important interview question. Lowest potential of the circuit. Of the entire circuit, the P sub, being shorted to the lowest, keep in mind, the lowest potential of the whole circuit. Why is that? And you're thinking, hey, this is grounded, right? How do we ground the substrate? Is we just flip the wafer and short a wire to the bottom of the wafer and then ground it? No, there's nothing on at the bottom of the wafer. We're not doing that. How do we ground it? How to ground the substrate? So these nodes are called it's called P-tap, or it's a body contact. Because this is called P-type substrate or P sub. Also, the substrate in integrated circuit design is also called body. That's the body of the chip. So that's why this P plus, you got a P sub. Like I said, if you have a P plus being doped over here, anywhere, doesn't have to be here, it can be anywhere on the whole wafer, and there's nothing else shorted or blocking this one from being connected to the P sub, then what's happening? Like what I just said, the P plus and P subs, they have the same type of dopant, but what's the difference? Higher concentration is heavily doped. It's more conductive. P sub is just a P type silicon wafer, all right? But anyways, they are very similar, but just a different concentration. But still, you put the P plus in the P sub, they are considered as shorted. So how do you ground P sub? How to ground the substrate? Yeah, ground here. How to ground here? If you ground this one, this is shorted to P sub, you ground the P sub, right?
Yeah.
That makes sense?
Yeah.
Does that make sense? Okay. So how do you ground this one? Could you ground this one? It has a little via here, right? You can connect to metal 1 and then metal 2, metal 3, and then wire bond it to the pad, to the pin of the chip, and then ground the pin. Then ground the P plus, and then ground the P sub. Does that make sense? So ground it. Keep in mind, not make a connection at the bottom of the wafer. Solder something. If you couldn't solder, just weld. Put it to the mechanical shop. Ask Jason to weld it. Or wire. So and then use like conductive epoxy or something to fix it in there, right? So in order to answer that question, because we have received all the chips from Moses, which is not doing this anymore, many years ago in my analog class, and so my senior son last year was trying to figure out. I don't know actually. I was trying to answer that question is if they do have a conductive epoxy because we received all the dyes and we purchased all the packages, right? So the next step is to put the dye into the package and do the wire bonding. Otherwise, moving around, you have to purchase the epoxy in order to do that, right? But my question is, if they have a conductive epoxy in order to, I don't know if they have to and why, but I was just thinking if they did that, if they have to use a conductive epoxy to do it, right? And then we did some testing and eventually figured out the epoxy is not conductive. And they don't have to use the bottom to short to it anymore, like ground or something. So it's not being shorted that way. So the only way, so we just proved that theory here, which is you ground the P sub by using the P plus through the wire bonding to the circuit. So we're going to introduce PMOS later, but now you know that this is called a body contact, which is a P plus and the P sub is a body contact. So if we have let's start with the N well first. So N well in the P sub, and this is grounded, right? Again, how did you ground it? Yeah, there must be a body contact somewhere, and then you ground the body contact to ground this guy, right? But now we have an N well resistor. Is a P, if you ground P, is it going to affect N at all? No. So you have an N-type material, have a P sub, even though they look not like this neat diode, but it is a diode. Okay. You are just using this N well as a resistor. Is it going to affect the resistance of this N well? Think about it before you answer that. So for example, you know this is like a diode, right? Parasitic diode. But N-type material just has a resistor connect to it, right? And you ground this guy, and you're trying to measure if this is still 1K ohms. Is it affecting the resistance of this guy? No, it's just still a resistor. And the diode is definitely not conductive because you just ground what? You just ground the anode of the diode, which is a P material, right? You ground it, right? Ground it. And remember, how much voltage do you need to make it conductive for the diode? Yeah, that's why you always want to ground the P sub to keep it low potential, so it's never never conducts current. Never got currents flow from the P sub to end of the N node in the circuit. Does that make sense? Because the substrate is a P-type material, so that's why you want to keep the P sub at the highest or lowest potential of the circuit. Lowest, why? So there's no current. And there's one important concept. Let's come back to this thing here. So in the real world, how do we make a diode? How do we make a diode? So this has to be grounded, right? And if you have P and what's happening here? Yeah, so I have a diode, and this is always grounded. I'm gonna use it. So this doesn't work, right? Then how do you do it? How do you make a diode here? Which one on top? Which one first? Yeah. So N plus P plus. And then what? Ground? Does that work? So this is -1, -2, -3, and then wire bonding, right? Right? And now I have a PN junction. So as a top view, that looks like this. NP. All right. If you ground P here, is it going to affect anything? No. So the current, if you give a power supply here, it's going to just make a current in that way. It's going to be a perfect diode. Okay. So you are using N plus to do what? Yeah. All right, that's how I make a diode on the wafer. And because this is a substrate, which means all the integrated circuits are fabricated on the same side. Right? If you have a P plus here, grounded, let's ground all the entire P sub. Right? But sometimes you need a multiple P pluses, everywhere, but not just one little P plus. You can imagine the dimension of the P plus over here is nanometer, just a few nanometers, but have a pretty big wafer. There must be resistance, right, to a long distance of the substrate. So you want to put a couple of or many P pluses everywhere and ground all the different places. So it's not generating a resistance in between the ground and the substrate. All right. A couple other things introduce. So an ideal diode IV curve. What does that look like? Ideal diode. So this is the voltage input, and this I. So when I'm talking about voltage input is plus minus V, right? Forward bias voltage. That's the polarity of the voltage. So which means the voltage, when the voltage is going that way, is increasing the potential here. Right? When the voltage is here, which means the voltage here is lower than this one. It's a negative voltage. Because this is 0, this is negative voltage. It is always V1 minus V2, right? Okay, if it's getting into the negative domain, which means V2 is larger than V1. Make sense? Okay, so in that case, what's the IV curve for the ideal diode? It doesn't even have the built-in potential. It should be like just turn on. Whenever you have a higher potential here, it should directly turn it on as the ideal diode. In real life, it's not, right? It has a built-in potential. So this is an ideal diode with VB. VB is just the built-in voltage, which is the threshold voltage. Still ideal, so it has a really sharp curve here, right? And this is 0.7 volts. What about the real diode? IV curve look like you open up, you purchase the diode and open up the data sheet of the diode. It's gonna show the IV curve, right? Or you can do, yeah, around the corner. And whenever you reverse bias it, it wouldn't be just 0 amps. There will be a lot of leakage here. And like that. And here is 0.7 volts. And the current here, the little current here, it's called IS, saturation current. So there are some current flowing backwards, but very tiny. But consider as just blocking the current flowing backwards. It's small.
Where do they measure IS on the data sheet? Because wouldn't it technically go to infinity as voltage goes to infinity, or is it?
It's going to break down afterwards. And not reversible. damage. It's just a regular diode, right? So what if, so that's why I'm going to introduce a different one. You probably will use it in analog as well. So Zener diode. The Zener diode, you use it as, you just intentionally break it down. It's reversible. Zener diode, a real, let's start with ideal Zener diode, right? Ideal Zener diode. It's still a diode, so it has a built-in potential. But however, no, Zener diode, if it's ideal Zener diode, we are treating it, it's not having any built-in potential. But what this one does is it breaks down at a certain voltage, reverse biased, when it's being reverse biased, like that, plus minus, right? That's a symbol of the Zener diode. It looks a little bit different compared to the regular diode. Anyway, and this is denoted as minus VZ. And why do we use a Zener diode? Where do we use it? So you can fabricate, when the company, the foundry fabricates the Zener diode, they put a different concentration of the dopants in there to make a different VZ, right? It can be here, it can be here. So this is adjustable, depends on how you make it. And in that case, whenever the voltage is over a certain voltage, for example, the Zener diode, the voltage rating is 0.3 volts, okay? So VZ is 0.3 volts here, all right? Whenever the voltage is higher than that, like 5 volts, what's going to happen according to the curve? So this is V, this is I, right? Is there any increase, shape, or shifting on x-axis dimension? No. So the VZ will permanently stay here. See, the VZ is not changing, it's not moving. So the curve is not moving there, not moving here. It's moving vertically down. So VZ is not changing, which is the reverse voltage is not going to change. However, what is changing here? Current. So what this one does is it's going to flow a lot of current in order to drop the voltage down to what? To VZ, which is built into the Zener diode. So it is able to stabilize the voltage to protect the circuit. If this one, so for example, it's going to stabilize at 0.3 volts, right? But whenever the voltage it becomes higher than that, it's going to draw a lot of current in order to drop that voltage down to VZ. So after that point, it's going to just follow that curve here, but not moving to anywhere else, right? Just stay at VZ, changing the current. If you're trying to increase the voltage, it's going to bring it back down to 0.3, but changing the current, right? So that's the ideal Zener diode. What about a ideal Zener diode with VB? Yeah, just like that, right? It's VB. What a real Zener diode looks like. So real Zener diode has a built-in potential, right? That's VB. And whenever you reverse bias that Zener diode, what's going to happen? It's like a regular diode, right? There will be a leakage. And at some point, and this is not vertical to X, right? There will be a little ramp here. That's still minus VZ. what's the difference? I mean, if you compare a regular diode and a Zener diode, that's a regular diode, that's a Zener diode. They look the same, huh? Yeah. If you reverse bias a regular diode and move the voltage backwards to over this point, it's going to break it permanently. Not reversible. This one is reversible. And you only operate the Zener diode that way, right? That's the purpose of the Zener diode, to stabilize voltage. It's not being used as a regular diode. Way more expensive than that one. You can buy a regular diode if you just want to use this part of it, right? You don't have to use the Zener. If you use the Zener, you are using this part of it. I was thinking, when you are going to give me a quiz? No quiz today. We'll do the quiz on Monday. Sorry for that. A few examples. I know some of them can be very similar to whatever you're going to learn in analog, but we have to cover it now in order to move forward with MOSFETs. Okay. As a real diode, no reverse breakdown. That's a real diode, but no reverse breakdown. So you are not doing that. Just permanently following that curve. Not breakable. So draw the VI versus VO curve. So this guy has a threshold voltage, which is 0.7. And after that, so this guy requires 0.7 volts in order to conduct the current. But after that, it's going to stay at 0.7 volts. Is that interesting? Yes. Yeah. So no reverse breakdown, which means when VI is pretty negative, it's not doing anything, right? It's linear. X equals to Y equals Y. X equals Y. Right? If this one is higher, this node is higher than this node, and this one will block any current flowing that way, you can just remove it. Okay, so voltage here equals the voltage here. No current flow. They're open circuit. This guy, no current, no voltage drop. So V over equals V. Make sense? That's why. For the negative domain, X equals Y, or VI equals VO. Any questions on this? Okay. What about here? VI start increase the voltage. Start biasing the diode. Before 0.7 volts, it's linear, right? X equals Y. Whenever it reaches 0.7 volts, this diode is going to clamp the two nodes at 0.7 volts. So what's happening here? I mean, you're thinking, yeah, 0.7.
Right, but can you adjust that, like when you make the diode, so you have one whose toggle is 1 volt?
It depends on the material,
Okay.
but I think definitely based on the doping concentration, it's changeable. But what's happening here? You are increasing VI, but here is not changing. How that works? How can you achieve that? This is increasing, but this is not increasing. But where are these voltages? They're being lost somewhere, right? Where? Yeah, the resistor. What's happening here? Yeah, voltage is dropping more voltage. If whenever you increase the VI, it's just injecting more current to the circuit, even though this one stays at 0.7 volts, but more current flows through the same resistor, just more voltage drop. But still dropped to 0.7 volts.
Would you break the diode if you didn't have the resistor in
Yeah, it's being broken really quickly. Yeah. That's why for the LED is a light emitting diode, right? Still a diode.
Yeah.
I mean, how to operate it? Yeah, you got your Arduino here, right? Have a pin. I usually always, not usually, I always have a resistor here connected to this guy and ground, right? So you can operate it, turn it on, or blink it. You always need a resistor for that reason, right? And you don't need a very high resistor here. You just need like usually 220 ohms to 1K ohms, that range. Depends on how bright you want this LED to be. But a couple hundred ohms will be good enough. Let's look at a different one. What if I rotate that diode? VO, VI, plus, minus, plus, minus. VI over VO, right? How to plot it? Whenever VI is positive, right, it's plus minus is positive, this guy is going to block all the current. So just remove it. It's not happening. It's not doing anything. So for the positive domain, VI and VO, what's the relation? Same. Okay. What about the negative domain? Whenever the potential here is higher, this is lower. That's why it's negative, right? Yeah, it has to have to reach negative 0.7 volts in order to conduct current in here. But before that, before negative 0.7, they are still equal. There's no current flow, no drop. No drop here, right? So that's why VI equals VO. After 0.7, it's going to be a flat line here, and the voltage here is negative 0.7 volts. I think it's the same. I don't think there's any difference. Where is the circuit loop? Where is the circuit loop? This, right? Is there any current flowing here? In here?
No.
Why? No load, right? So it's open. Why is this not open? Yeah, it looks like open. You draw it like as an open circuit. It's not. It's a battery. Just to tell you, it's a battery. Yeah. What's next?
Wait till analog comes.
Yeah.
Are similar. Whenever this one is larger than 0.7, then current flow that way, right? And then here becomes 0.7 volts. Whenever this voltage is lower than negative 0.7 volts, this one is conductive, so the current flows that way. So the voltage here becomes negative 0.7 volts. But whenever the voltage in between these two voltages, none of them are conductive. So in between 0.7 and negative 0.7, no, they are equal. Yeah, it's just linear. But after that, whenever this is higher, make sense?
Yeah. What is the practical application?
Oh, quite slim again. I can show you pretty soon. Let's take a look at this one. Electric shock diode? No. Static discharge, electric static discharge protection. Forgot the name, whatever. So whenever you got static shock, static voltages on your hand, you touch the chip, it's gonna input a really, really high voltage, sometimes 20,000 volts. You got 20,000 volts on them on your finger. Don't believe that? But yeah. Yeah. We can, but sometimes it's just so time consuming. Yeah, you ground it. But you know, in practice, in my lives, we never did that. Probably it's damaging 1 out of 100 chips. If it's damaging like 10 out of 100, it's pretty significant, so we probably will do it. There's 1 out of 100. If I have 20 students, probably after like every 4 weeks, they'll grab a chip and tell me like this is not working. We just throw it in the trash. But we don't have to wear it every day, every time. Sometimes you couldn't move around. You should if the parts are expensive, but if they're only like a couple cents.
You have started.
Right. Chip Act. Yeah, I'm trying to apply for some funding there. Here's the chip, okay? And these are the pads I showed you, right? Remember? The pads being wire bonded. And these are the integrated circuits. So these immediately, so these are just metal pads, right? And immediately inside the pad, here, right, here's, for example, this is the V in. This is V in. Okay, the voltage in, right? Voltage in. It's like the static voltage in on your hand, voltage in. And if I model that, if I draw it here, like V in, and just model a little resistor here, and that's a chip, whatever inside the chip, right? And you need the ESD diodes here to protect your circuit. And you have to connect it that way, plus minus, and you short this one to 20 volts, for example. If it's a 20 volt chip, at the highest potential in the circuit. Why is this protect the chip? If suddenly you got a 20,000 volts here, very short period of time, the power is low, so it's not necessarily breaking that diode. Just a very sharp peak. So the 20 volts is actually a power supply, right? 20 volts is powered up. So if you draw V in over V out here, what the curve looks like. It's very similar to the previous ones, like this one. So if the voltage here is very high, it's higher than 20 volts, or 20.7, if this is 0.7 volts, right? This diode only becomes conductive whenever the voltage here is higher than what? 20.7. And then it will be clamped at 20.7. Is that correct? Why? Even you have a 20 volts here after the resistor, it's still 20.7. Why? No, it's because of this guy. Why is that? Remember, the diode is going to clamp it at 0.7 volts, right? Period. It's always 0.7 volts. What about the voltage source? Why it's called a voltage source? Yeah, is that changeable? If you don't change it, no, it's just 20 volts, right? It's permanently 20 volts. You couldn't change it. So this becomes two battery cells in series. So what's the voltage here compared to ground? So what's the voltage potential difference between these two nodes? 20.7. Can you make it larger? No. Permanently 0.7, permanently 20. So what if even though this is very high, it's going to dissipate the power to the resistor just by dropping the voltage here like crazy. Eventually, it's being clamped at 20.7 volts. It's not increasing anymore. So we can.
Why does the 20 volts not mess it up by backdragging?
Yeah, because reverse breakdown voltage is higher than 20 volts.
Oh.
What about this one? So you are thinking 20,000 volts is very large, and you are thinking negative 20,000 volts is very small. Is that correct? It's not like temperature, right? 20, like 200 Fahrenheit is very hot, very high temperature, and negative 200 Fahrenheit is very low temperature. It's not like that. Negative 20,000 volts is super high energy as well, or super high potential, which is a different polarity. It's still like that much potential, can kill someone. It has enough power here. But anyway, so whenever this one becomes negative 20k volts, what's happening? What's going to happen here? So this diode will play some role here. Why? So if this potential becomes very negative, right? Very negative voltage. Ground is not as low as the potential anymore. It's ground is 0 volts, but you have negative 20k volts here. What's going to happen? Yeah, so current is going to flow that way, right? And then what? The diode will clamp the voltage difference between these two nodes at. So what's the voltage here? What's the voltage here?
Oh, yeah. If
you were to implement this circuit, would you give the bottom diode negative 20 volts, or would you just leave it around?
You just don't have that negative 20 volts in the circuit. But why negative 20 volts? No, you see, now you have this one very close, still very close to ground, which is desired. Here?
Yeah.
Oh, maybe. The cost is high. I have to design a lot of things in there, but you do need something to protect it. It's doable, but we don't do it. Yeah. All right, so you just asked about the question, why do we use it? And now there's how you use it, where you use it, right? And I think, do we have that? Oh, we don't have that in the lab. Probably will add something to it. Just have the tutorials on my website. I'll just refer it to you after you design all the LU. And probably ask you guys to make all the paths and put the LU into the path frame and connect to the path. So in that case, if you are doing the paths, I'll ask you to do the ESC diodes as well. So you can physically lay out diodes in there. Right? I have to do this anyway if you are doing senior sum with me. I have to do this anyway. For each one. Everyone can be touched by our finger, right? Or can be access to some. If you plug into the board, even though it didn't directly touch the pin, but still, there's something can be directly shorted to it. If you touch the board and the board got a short circuit to any pins, it's going to damage the whole chip. All right, there's something else I have to cover on Monday. So you are still not super ready for the homework for today, but after Monday you will be. You can start working on it if you like.